part 2. Okay, well, as I said before, I'm not giving all the details. I mean, I have already used some propositions, some things that I haven't proved, and now I will use more propositions that I won't prove. But in spirit, they belong to like other areas of math. Okay. Well, there is a particular proposition that I will use that comes from singularity theory, and I would really like if somebody of the students doing the course want to do a presentation about it. It will be nice for me. Okay. So well, I will point it out when I get there. So first of all, just I want to recall the statement of the theorem. So the theorem is this. The theorem that I started to prove the last class is this. So let E be a compact complex manifold D a divisor, a smooth divisor, a codimension 1, a complex closed submanifold, right? And F from E to P1, a holomorphic map. Right, and such that so it has F restricted to D is a submersion, right? No. F restricted to D is. Wait a minute. Okay, so holomorphic such that. Okay, let's say holomorphic. Okay, let's see inside P1 be the finite set of critical values, and let's fix a point infinity in P1 that it can be inside C, it can be a critical value. In fact, we will always tend to pick it as a critical value. Okay, let's fix this guy and assume that. So assume that F restricted to D has no critical value in C, P1 minus the infinity. Okay. And assume also that F it has only isolated critical points in E minus the fiber at infinity and the divisor. Okay. So then, for every regular value, for every B in P1 minus C and infinity, the homology of E minus the fiber at infinity and the divisor relative to a regular fiber is 0 and free finite rank in the middle part. Okay, here this n is the dimension of E. So here is complex manifold of dimension n. Okay, so this is the theorem that I already started to prove, and what I already did is to prove this theorem in the particular case where all these critical points are non-degenerated critical points, right? So I already did that. So here remark. When all critical points are non-degenerated, the theorem holds. Okay, so an example of this kind of situation is when we take a pencil of hyperplane sections, right, of a projective variety. So in particular, we already know that whenever the pencil is good enough, for instance, is as good as to produce a function f that only have isolated non-degenerated critical points. These are the ones that we call the Lefschetz pencils. We know that this, the Lefschetz theorem, that is the corollary of this theorem, is already true, right? So I want to do a picture, just a picture. So something like, so what do we conclude? Is that, well, maybe I will do the picture later. So in the case we have, so for X, a smooth projective variety of dimension n, and let's say Y and Z a hyperplane, general hyperplane sections. Okay, we already know that we have, we have the following sequence. So here we have Hn x minus z relative to y minus z. Here we have Hn of x minus z. And here we have xn of y minus z, but we already know that this is 0, right? Well, I am assuming that, I already proved this theorem. I mean, I have already proved Lefschetz's theorem, so I can use it in this case, so I can conclude this in this particular case, you know? I mean, I'm not doing like a circle argument. This is what I want to say. Here, Hn minus 1 of y minus z. And here, Hn minus 1 of x minus z. And then the relative that is also 0. right? So we know that this guy is 0. We already know that this guy is free. Well, all these guys are free, right? This guy and this guy. This, well, we don't know about this. Okay, so the thing is that we know how to produce the generators of this relative homology group, right? Because the proof tells us how to do that. We just have to pick the whole family to look at the critical values. For each critical value we see at each isolated critical point, we isolate the topology, I mean the homology group, the relative homology group of a neighborhood of this critical point. And then, since we're in a Lefschetz pencil, because these guys are general, right? We know that that each generator of this homology group will correspond to some real ball in this neighborhood, right? So, okay, so now I will draw a picture. So in particular, for instance, when if this guy is 0, I mean, so if Hn minus 1 of x minus z is 0, then we know how to produce the homology of this guy. I mean, this is the hyperplane section, right? The affine part of the hyperplane section. So we know how to construct the generators of the affine part of an hyperplane section of a projective variety, for instance, the projective space, right? And it will correspond just to taking these generators and see their boundaries. And the boundaries, we know what they are. I mean, they are like real spheres, right? So if this guy is 0, Hn minus 1 of yz is generated by the boundaries of the generators of this other group. Okay, so, well, now I will draw a picture. So we will consider a family of curves. So let's take the dimension of x equal to 2, a surface. Okay, so in a surface, well, I will take a family of genus 2 curves. So this is just a picture. It's not nothing. I won't do any count. I won't take any example. I mean, so the picture is like this. So we have here a regular fiber. Okay, it will be a genus 2, a smooth curve. Okay, but we are in the affine part. Okay, so let's suppose that this is a hyperelliptic curve. So let's say we're removing 2 points. Okay, so it can be taking the family of y squared equal f of x, where f has degree 4. Right? We're removing 2 points. This is the affine part. Okay, and what I'm saying is that I can produce this homology, all the generators of this guy, coming from here. Okay, so the idea, the picture is like this. So we know which are the generators. For instance, we take, well, let me just choose them wisely. Okay, this guy. This is another guy, another generator. Maybe I should use colors. Well, it's okay. It's another generator. Here we have another one. And since we removed 2 points, we can take one extra generator here, right? Okay, so what is happening? So here we have the vibration, right? Here we have F. Well, and here we have the regular value B. So here we're in C, that is P1 minus the infinity. Okay. So what is happening is that whenever we go to a critical value, so for instance, let's say here, critical value is C1, maybe a little bit further, this cycle will vanish. So what do I mean by that? The situation will be something like this. I don't know, this, you can see this? Can you see this? Yes? Can you see it? Yeah. Maybe bigger? It's okay. Okay, so here the fiber will be singular, right? So it will be something like this. We still have these 2 removed points. And what is happening with this is that this cycle is deforming into a point. It's degenerating into a point. Okay. So this thing is exactly the generator of the relative homology in this ball that we choose around the critical point. You see, this will be the boundary of the real ball, and this thing will be the real ball. And these things are called Lefschetz thimbles. This is what is called a Lefschetz thimble. So these generators of the relative homology are called Lefschetz thimbles. Okay, and so the thing is like this. Then, for instance, we will have something like this here. Let's say, and here we will have a singularity, right? I don't know, here, maybe here. We will have a singular fiber like this. And here another fiber will be something like this. Right? Something like this. You see, and here we will have the last fiber. So the thing is like this, you know. So, and all these symbols will be generating the homology, the relative homology of the whole family relative to this regular fiber. Okay, so this is the situation. So you have here this singularity, another critical value here, another one here, and like this. Okay, just a picture. And these guys, the boundaries of the Lefschetz symbols that will generate the homology of the affine part of the regular fiber, these are called, these boundaries are called vanishing cycles. Vanishing cycles. Okay. Okay. So, in order to, if you remember, in order to finish the proof of this theorem, we have already reduced everything to the local problem, you see. So, this local problem is easy when the singularity is non-degenerated, but in general, it's not that easy. So now I will state the theorem that we need to prove in order to finish the proof of this result. So what is left to prove is the following theorem. So let U inside Cn be an open set containing 0. Okay. And let F from U to C be a holomorphic function we will assume that it sends 0 to 0 and with f of 0 equals 0 and having an isolated singularity at 0. Okay. So we want to prove that if B epsilon contained in U is small enough, let's say small enough open ball centered at 0, and the rho contained in C is a small enough disk centered at 0 also. Then for B in the boundary of the disk, a regular value of F, the homology of B epsilon bar intersected with F inverse of B rho bar, relative to their fiber at B. This is free for k equal to n, 0 for k different from n, and this mu can be computed mu is the Milnor number of the singularity. So mu is equal to the dimension as complex vector space of OCN 0 mod the ideal generated by the partial derivative of f. Okay, here what I mean is this is the space of germs of holomorphic functions defined in a neighborhood in some neighborhood of 0. Okay, so using this, we already have everything in order to compute the relative homology of any family of this type. We just need to isolate each critical value, compute the Milnor number at each point, and then we have to sum these Milnor numbers. Okay. Okay, it's clear? Is it clear? Okay, so in order to prove this part, that is the local part, we will use the theorem that we want to prove. But in the non-degenerated critical points case. So what's the idea of the proof? Okay, so here proof. Okay, so first of all, let's assume the following situation. Let us assume that f is a polynomial I'm using z and x. I will use x for the variables here. Okay, so let us assume that it's a polynomial. This is much particular than this other situation. And let's write it as a sum of homogeneous polynomial, right? As a sum of homogeneous polynomials. Okay, so we write f as fd plus 1 plus up to some fn, okay, where each fi is a homogeneous polynomial of degree I. Okay? So since we are assuming that f of 0 is 0, we know that it starts from a positive degree here. Okay? And let us assume also that the projective hypersurface, so here let's say x1 xn in Pn minus 1, such that Fn of x1 to xn is equal to 0. Let's assume that this projective hypersurface is smooth. Okay. Okay, let's assume all these things. And now we will prove the result in this case. Okay? So first of all, we will prove it in this case particular. Okay, so now for every u in Cn, define the following function, the following polynomial, right? Fu of x1 to xn, define it to be as f of x1 to xn minus u1 x1 un xn. Okay, so this is a deformation of f by a linear map. Okay, so which are the critical points of fu? Okay, so let's say x in Cn is a critical point of fu if and only if the partial derivatives of f at x correspond to the ui's, the entries of u. Okay, it's just computing the derivatives of this map, right? So, and furthermore, it is a critical point if and only if this, and it is a here degenerated critical point if and only if this happens and u is a critical value of this map, the gradient map, right? The partial derivative of f with respect to x1 till xn, right? That goes from Cn to Cn, right? So we know that by Sartre's lemma, we know that there are a lot of regular values of this map. So if we choose one regular value, we see that every critical point of fu will be non-degenerate, right? So for every regular value u of the gradient of f, fu has only non-degenerated critical points. Okay. So now we just need to apply the theorem to fu. So how do we do that? We just need to check some things. So first of all, what we have to do is to extend this map to a map in something defined over something compact and smooth, right? So we have it defined over Cn, so we can homogenize it in order to define it over Pn, but whenever we do that, the map is not well defined, so we have to do this blow up in order to get something that is well defined, holomorphic, and whenever the the divisor is non-singular, the divisor where it is not defined is non-singular, we will have that the map induced by the blow up will be well defined and will be a submersion restricted to the exceptional divisor, right? So that's why I am asking for this condition here, that this be smooth is in order to guarantee that the divisor at infinity here will be smooth, right? So let fu. So what is fu? Fu is fu of x0, x1, xn. It will be equal to minus x0 to the n minus 1 times u1 x1 plus un xn plus x0 to the n minus d fd plus x0 fn minus 1 fn. Right? This is the homogenization of this map. And what will be the blow up? The blow up will be this is Pn tiled. That is the set of points. So let's say x0, xn, comma, t0, t1 in Pn times P1 such that so it's T1 Fu is equal to T0 x0 to the degree of this thing, n. Right? And the map, the holomorphic map, is just the projection in the second coordinate. Right? And whenever we restrict this to the divisor, the divisor where Fu is not well defined, we will end up exactly in Fu of 0 x1 to xn, and this will cancel all this part, and it will just remain this part, the last part. Okay. So now we can apply our theorem in our particular case. So we can apply the theorem to this map that I will call it just F-tiled. To F-tiled, and what do we get? And so we know that the relative homology of what? So it will be the whole fibration space minus the fiber at infinity and minus the divisor, right? So whenever we remove these two things, we're just going back to the domain of Fu, that is Cn, right? So it's the relative homology of Cn relative to the fiber, to a regular fiber here. F of Fu, right? So relative to F inverse U of some regular value here. So let's say, so we can choose it to be, well, it doesn't matter, R. So we already know that this is free. for k equal to n, and 0 for k different from n. Right? And what is mu in this case? We know that mu is the amount of critical values, of critical points of fu, right? So if the amount of critical points, but which are the critical points? The critical points are exactly the points that satisfy these equations, right? So we're just looking for the amount of preimages of this gradient map, right? It is the cardinality of this, right? And so well, here I will recall this result from singularity theory. So proposition okay, so this is valid for germs of functions, of holomorphic functions. So I mean, this you can find the proof of this in chapter 5 of the following book, Singularities of Differentiable Maps, volume 1. This is a book written by Arnold, Gusein, Sade, and Barchenko. Okay. So the proposition says that if you, I mean, how do I write this? I mean, if f, let f from u to c, sending the 0 to the 0, be a holomorphic function, then for a general u in C close enough to 0 and different from 0, then the, well, I will write this, I will give it another name, G. Then the cardinality of G inverse of U is equal to the, what it should be, the Milnor number, OCN 0 over G1 G. Okay? So the thing is that whenever you're getting closer to U, all the preimages will lie inside this domain where the map is well defined. And you can count them, and it's exactly this number. Okay, and this is non-trivial. It's also not that hard, but it's long. I mean, you have to prove a lot of the small, simple propositions in order to prove this. This is why I'm skipping this part. And this is what I would like to see if some of the students is motivated in order to read the book and present it. Okay, so after this, we already have the last part of the result, right? I mean, we already know that this is the Milnor number, right? Okay, So how do we end the proof? In order to finish it, we just need to relate this fiber. No. Gn to Gn are the coordinates of this. Sorry, this is.
There is G0 equal to 0.
G0. Yes. Yeah.
U is an open set in
Cn. This is open in Cn. Open. Containing 0. Okay. Yes. Okay, so now we have to relate. Well, there is an observation that we can do here. If we look at the long exact sequence of this pair, we have this isomorphism here with the boundary map, right? I mean, the isomorphism is in this direction, and because just the homology of the affine space is always 0, right? Well, you have to take care about if k is equal to 1, but it doesn't matter. I mean, for k equal, the problem is when k is equal to
That is reduced homology.
Reduced homology?
Yes. And the case 0 is 0.
Yeah, the case 0 is like super easy to see. So we won't care about that. Okay, we will assume that k is bigger than 1. Okay. Okay. So the only thing that we have to do now is to relate this homology of this fiber with the homology of this relative thing, these balls, that we want to compute. So now, for k different from 1, so we have that the relative homology of these balls so here by excision we know that this is isomorphic to the global thing, right? Right? And again, the same argument gives us this other isomorphism. So we just need to relate two regular fibers, but for different values of u, right? And if we prove that these fibers are isomorphic, diffeomorphic, we're done, right? And this is easy to see. So consider the following map: f that goes from Cn times Cn to C times Cn, and takes the point xu to fu of x u. Okay. So again, we can. This map is not proper, right? The problem is in this coordinate, the first coordinate. But again, since we already have all the hypotheses in order to produce this projectivization of this map that is well behaved, in order to use, for instance, Ehresmann theorem, we can do the same thing with this f, this big F. We can projectivize it in the first coordinate and then we can do this blow up thing, and we can apply Ehresmann theorem to this. Okay, this is what I'm saying. I mean, we can add something at infinity in order to be in the setting of Ehresmann theorem, and whatever we are adding, we can, whenever we restrict to this thing that we're adding, we're also having a submersion, so we can get the result. I mean, get the vibration of the affine part. We can remove it from the vibration. So if we consider this map, so just by doing a simple computation, we see that a point xu is a critical point if and only if it's a critical point if and only if this nabla of f of x is equal to u. Okay, you just need to compute the partial derivatives of this thing. Okay, and so IE, so let's say x let's say BU here is a regular value of f, big F, if and only if B is a regular value of FU. Right? Because remember that the critical points of FU are exactly the points that satisfy this equation. Okay. So we're almost done. I mean, well, the only thing that we have to check now is that there are some regular values, and obviously they are. And then whenever we remove the critical values, the thing that we obtain here is connected. And this is also true because the set of regular critical values is algebraic, right? The complement will be connected, okay? And the only thing that we have to check now is that the point, let's say BU is a regular value, and also the point B0 is a regular value, right? B0 will correspond to the fiber of F, the affine fiber of F, right? And well, by a hypothesis, we are taking B such that BU is a regular value, and also B we take it different from 0. I mean, we will have a regular value also of 0. I mean, of F0 of F, right? So we're done, right? So since let's say BU and B0 are regular values of F, then by Ehresmann we have that this FU inverse of B is diffeomorphic to F inverse of B. Okay, and we're done. in this particular case. So we proved the theorem, but in the case that f satisfies all these properties. It is polynomial, and at infinity it is smooth. Okay. So in order to finish the proof, we need to reduce ourselves to this situation. Okay, and this is something that we can do using the following result from several complex variables. So this is other result that I won't prove. It's much simpler. I will just give a reference for this. So, theorem. So the reference is, you can find it in the following book, Local Analytic Geometry. What's the name? Basic Theory and Applications. And it's the authors are De Jong and Pfister. This is theorem 9.1.3. Okay. Okay. What does this theorem says? It says that let f be in the ideal generated by the variables. Let's write it in this way: x1 to xn inside the ring of germs of holomorphic maps from Cn to C. So it's just a holomorphic map that vanishes at 0. Okay. So let f here, and suppose that for some k, the ideal generated by the variables to dk plus 1 is contained in the maximal ideal times the Jacobian ideal. Square. Okay, so assume this, and this always exists. You know, this k always exists, because well, you have in complex variables you have this Hilbert-Nullstellensatz theorem. So you know that if you look at the 0 set of this ideal, you will get just 0, just the origin, right? So the radical of this ideal will be exactly this, the maximal ideal. Again, I mixed the right. So the radical of this thing will be exactly this ideal. So since this is Noetherian, you will get that this k exists. You know, this is a very easy exercise, right? Okay, so suppose that you know this k. This is what is this saying. Then for every g vanishing at 0, such that f minus g belong to the maximal ideal up to k plus 1, there exists an automorphism phi, an automorphism of this. I mean, by this, this means that there exists a change of variables of Cn locally at 0, such that f composed with phi is equal to g. So what this means is that whenever you're looking to some germ of analytic variety, you can find a change of coordinates such that it is equal to some like good approximation of the function, right? So this kind of a result in the direction of classifying the germs of analytic subvarieties, well, that are defined by just one polynomial. I mean the analytic hypersurface, right? So and so using this we are done. You see, because you take f to be the function of the theorem, and you look at its expansion and at his Taylor expansion around 0, right? And you will see that up to some point you can truncate it, and the variety that you will get, the function, it will be, every fiber will be diffeomorphic. I mean, not diffeomorphic, biholomorphic to the one corresponding to f, right? So even if in this local setting, you can reduce yourself to a polynomial function. And after that, if the infinity of this polynomial function is not well behaved, you can add like one Fermat, a very high degree Fermat, much bigger than the degree of your polynomial that you obtained truncating it. And this theorem also says that it won't change locally whenever you add it. And at the infinity, it will be smooth because you constructed it in this way, right? So just to write this down. So for the general case, take G a polynomial such that f minus g it's inside this x1 to xn to the k plus 1 contained in here. And then add and then replace f by g plus, let's say, x1 to m plus xn to m for m bigger than the degree of g. Okay, and this is smooth. Okay, this is smooth, bigger than the degree of g and bigger also than k plus 1, let's say. Okay, and then you're perturbating this by something that is again inside this ideal. So again, there exists this B holomorphism local that transforms f into this other map that is polynomial and it's well behaved. Okay? Clear? Do you have questions? Clear? Good. Okay, so I will just finish this class with a simple account on how we can use this theorem in order to compute the the rank of the middle part homology. Okay, in fact, we can compute it. I mean, and that's something we can do in this general setting. It's something that we wouldn't be able to do if we were just using this Lefschetz pencil thing that is just existential. So corollary. So let X container in Pn plus 1 be a smooth degree D hypersurface of the projective space, and then we can compute the middle homology of this. It's free and it's isomorphic to this number e minus 1 to the n plus 1 minus e minus 1 to the n plus d minus 1 to the n minus 1, and so on, minus 1 to the n d minus 1 plus alpha n, where alpha n is equal to 0 if n is odd and 1 if n is even. Okay, so we are computing the missing part of the homology of an hypersurface. We already know that all the others are 0 or C, and this is the missing one. Okay. Okay, so proof. Okay, so first of all, note that the homology is independent of the polynomial equation. You know, it just depends on the dimension and the degree, right? So, and this follows from Ehresmann's theorem, right? Note that if we take the following family, so consider x to t. So take t inside the space of whole polynomial equations x0 to xn plus 1 of degree d, right? This is a vector space. It has a Zariski topology because it is isomorphic to C to something, to C to the n plus 1 plus d over d, right? That is the amount of monomials of degree d in n plus 2 variables. And you can consider T the open set consisting of polynomials that define a smooth hypersurface, right? This is open because it is just defined by this Jacobian criterion, right? So this is the parameter space of all smooth hypersurfaces. Okay, and next, what will be? It's like the universal family of this, right? So X will be the set of all x, comma t in Pn plus 1 times t, right? Such that X is inside the hypersurface defined by T, the xt, right? That it's just T equal to 0, right? Again, this is proper submersion, and so by Ehresmann theorem we know that it is a locally trivial fibration, and then you can pick any fiber in order to prove this theorem, right? So this is a proper submersion, and so by Ehresmann, f, well, let's call this, let's say pi inverse of B1 is isomorphic to pi inverse of, let's say T1, T0 for a pair of points into. So we just need to prove that for one smooth degree D hypersurface, okay? And which one we will pick? Fermat. That is the simplest one. Well, in some sense. Okay, so we can restrict ourselves. So we can assume that X is Fermat. So X is Xn D, the set of points such that x0 to D plus xn plus 1 to D is equal to 0. Okay? Cool. So now let's prove that, first of all, that it's free, it's torsion free. The homology is torsion free. So for n, so let us prove it's torsion free. Okay, so for n even, so first case n even. So for n even, take the Lerey-Thom-Geisen sequence of the pair Pn plus 1 minus x. Okay. So what do we have? We have here Hn plus 2 of Pn plus 1 minus x. Here we have Hn plus 2 of Pn plus 1. Then the intersection map Hn of x, then Hn plus 1 of Pn plus 1 minus f minus x, and then Hn plus 1 of Pn plus 1. Okay, and we're assuming n is even, right? So if n is even, n plus 1 is odd, and this is 0. Right. Also, we know that all the homology groups of an affine variety that is obtained from removing an hyperplane section are 0 except the middle one. So this one is also 0. Right. This one is non-zero. It's free. Right. And we already know that this is free also. And so this is free, right? Cool. So for n even, we already know that it's free. And for n odd, second case is n odd. Again, consider the Lerey-Thom-Geisen sequence of the pair x relative to x minus a hyperplane section. So it will be x minus So I will write it xnd minus xn minus 1d. Okay? So this xn minus 1d is what appears when you intersect Fermat with hyperplane, let's say x0 equal to 0. You will get another Fermat one dimension less. Right? So what do we get here? We have here hn plus 2 of x and d. Then, no, wait. No, I want to do it for xn plus 1, xn plus 1, xn. Okay, n plus 1. Here I have hn of x and d, intersection map. Then I have hn plus 1 of xn plus 1d minus xnd. Okay, so I'm assuming that n is odd, so this is odd, so this is 0, right? Because we already know how are the homology groups of any hypersurface, right? This is 0, and this one is free. So this guy is also free. Okay? Okay, so it's free. Now we just care about the rank. Okay? We want to prove that this is exactly the formula for the rank. And we just need to do an induction. So in order to compute the rank, let us proceed by induction. On n. Okay, so the first case is n equal to 1. So for n equal to 1, the curve. Okay, n equal to 1. What do we know now? We know that the h1 of x minus the infinity, right? Let's say the infinity, I don't know, x infinity. We know how to compute this thing, right? Why? Because we can pick up, we know that this is isomorphic to h2 of x. I should put, I didn't want to do this, but I will have to. x0 d. What I mean by x0 d is the zero-dimensional Fermat, right? This means that I'm taking here x0 to the d and x1 to the d. And when you factor this out, you will get exactly d factors. So this corresponds to d points, right? So I'm removing here d points at infinity. Okay, and this will be h2 of d minus x1d relative to x1d minus x0d. Right? Is this correct? No, sorry, I'm talking nonsense here. No. Yeah, no, this will be C2. Right? I mean, you're considering now which family? The family is given by taking C2 to the point x1 to the d plus x2 to the d, right? x1 to the d to c2, right? The regular fiber would be let me write this here. So yeah, so the map here is like this, right? It's F from C2 to C, right? And takes x1, x2 to x1 to the d plus x2 to the d, right? And we are looking for a regular fiber of this, right? So a regular fiber would be, for instance, f minus 1 of minus 1, right? It will be exactly the set of points such that x1 to the d plus x2 to the d plus 1 is equal to 0, right? And the homogenization of this will be the point such that x0 plus x1 plus x2, to the d, is 0. That is Fermat, the Fermat curve, plane curve. So this is the affine part. So this is exactly x1d minus x0d, right? And the whole vibration, the whole family, at the infinity, whenever we construct the vibration, we will have to produce this f tilde that will go from P2 tilde to P1. We will have at the infinity of this point, we will get x0 d, and and that's all. No. At the infinity, we will get a P1, right? Like the P1 that we're using to compactify this. This is what we will get at infinity, the divisor at infinity. And the exceptional divisor will be x0d times P1, right? So we're good. We're in position in order to apply the theorem, and we can compute the first homology of this. That is the middle homology of the curve, of the affine curve, right? So we already know that h1 of x1d minus x0d is isomorphic to C to something. What is this something? This something is the dimension, is the Milnor number, right, of OC2 0 over the partial derivatives of f. But what are the partial derivatives of f? Just x1 to the d minus 1 and x2 to the d minus 1, right? And so what are the generators of this vector space? Just monomials where the multi-degree in each entry is less or equal than d minus 2. So this is exactly equal to d minus 1 squared, right? You have the freedom of choose the exponent of the monomial, and in each entry you can choose it between 0 and d minus 2. So you have d minus 1 options for each variable, right? And you have two variables. Okay? So we already know this part. And on the other hand, we have this isomorphism because of the because C2 is contractible. You just have to look at the long exact sequence of this pair. And so we know this. Yeah, well, no, this is the one that I was computing, right? The theorem tells us how to compute this, the relative one, but it's isomorphic to this one. Okay, and after that, since we know that we have removed exactly d points of this curve that is smooth, right? This implies that the h1 of x1d is just c to the d minus 1 squared minus d plus 1, right? This is exactly the formula for n equal to 1, right? In particular, from here you know that the genus of any smooth plane curve is d minus 1 over 2, right? Okay, and now the inductive step. Now for n bigger than 1, consider which sequence? Consider the Lerey-Thom-Geisen of xnd relative to xnd minus xn minus 1d, and you will get here hn plus 1 xnd. Here you have h n plus 3, I think. Yes. H n plus 1. Well, of this is xn. I don't know. Here I have the relative. This is the big one, it goes to the relative and comes from this one. Hn plus 1 of xnd minus xn minus d minus 1d, right? And this is 0. Here we have hn minus 1 xn minus 1d. Here we have hn of xnd minus xn minus d minus 1d, right? hn xnd and hn minus 2 xn minus 2d, and the last one is 0. Right? Okay, so now we just need to separate in cases if n is even or odd. So for n, let's say n even. So for n even, we know that this is 0, right? We know that this is one-dimensional, and this one is the one that we can compute. So how do we compute this? It's the same thing that I explained before, right? So now you're taking, instead of f in two variables, you're taking f from Cn plus 1 to C given by f of x equal to x1 to d and to xn plus 1 to d, right? And we're looking for the preimage of minus 1, that is a regular value. And again, we know that the homology of this thing is isomorphic to z to the dimension of OCN0, over the partial derivatives of this equation, that is just x1 to the d minus 1, xn plus 1 to the d minus 1. And so this is d minus 1 to the n plus 1. Right? So this is c to the d minus 1 to the n plus 1. And this is the one that we're using the induction hypothesis. So this is c to the d minus 1 to the n minus blah, 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 minus 1 to n, d minus 1. And since n is even, this guy is odd. And so we're adding nothing else. And so we have this guy minus this plus 1. Right? So we're done in this case. And for n odd, we will have now that this guy here is z, this guy here is 0, this guy is the same thing, and this guy will have a plus 1 here that will be cancelled with this one. And so we will get the formula. Okay? So cool. Well, questions?
¿Por qué el T es conexo?
What? ¿Por qué quién?
Cuando usted probó que todas las hipersuperficies de grado E son diffeomorphas.
It's because just it's an algebraic variety. I mean, it's you take the affine space, this T, right? When you take this family, xt, right? And this is contained in some affine space, right? But this is defined by an it is the complement. It is open, Zariski open. It is obviously connected. It's much more than connected. It is irreducible, right? You cannot separate this guy into two. You cannot even write this guy as a union of two proper open closed subsets.
How do you describe T?
T is the complement of a bunch of equations. It's the complement of an algebraic variety, right? So you agree that the complement of an algebraic variety inside a fine space is always connected. It has codimension at least 2 real, and it will be of codimension much bigger than 2 real, because it will be the intersection of a bunch of relations, right? It's just taking the equation, taking the partial derivatives, and take all them equal to 0. So you will have at least, I don't know, n plus 2 equations, right?